Good morning, good afternoon, or good evening, whenever you happen to be joining me. This is Dr. Molly, and I am so happy to be back with you today. I've been missing you very much, and I know we're in very uncertain times, and just glad to be getting back to some structure and getting to share with you my love of psychology. So hop aboard, we're getting back on the train. So today I'm going to be able to talk to you about the biology of behavior. This is sometimes content that students feel a little iffy about if they did not have a great experience with science in high school. It's one of my favorite chapters. It harkens me back to the time when I was in medical school and studying to go to medical school. And in gross anatomy, being able to do dissection and learning about the brain, and when the brain becomes diseased from strokes or from Parkinson's or from MS, what's going on with our neural system. So I'm really excited to share my passion of neuroscience and the biology of behavior with you. So as always, I'm going to start with a roadmap. Where we'll be going. So we're going to start talking about the nervous system, and I'll start talking about neurons, and then we're going to move on and talk about the hormonal systems and the endocrine system. We're going to then talk about the different tools of discovery that have been used to understand the brain and its structure and function. We're going to talk about the older brain structures, the brain structures that we have in common with lower mammals and other animals. We're going to then talk about the cerebral cortex, the part of the brain that really develops and makes us human, and with all of our amazing abilities. Well, then we're going to talk about how our brain is divided into a left and a right hemisphere connected by the corpus callosum. And I'll talk to you a little bit about that in the next lecture. Then I'll talk about genetics and evolutionary psychology and this understanding of how biology impacts the way that we behave. So that's where we will be heading today. So Dr. Myers and Dr. Dewall start us off with a question. So why are psychologists concerned with human biology? I'm sure you're thinking, I didn't know I was going to be in a biology class. Well, everything that's psychological, every idea that we have, every mood that you have, whether you're happy or sad or angry, every urge that you have, whether it's for hunger or sex, everything psychological is biological. And biological psychologists study the links between biology and our behaviors. So what are neurons and how do they transmit information? Well, neurons are nerve cells. They're the building blocks of our nervous system, and they consist of different parts. What I want you to do is I want you to hold your hand up with your arm extended. This is kind of a kindergarten trick that used to help me remember when I was in medical school, the different part of the neurons. So the cell body is the cell's life support center. And so on your hand, imagine that the cell body is where your palm is, right? So think about the cell body being your palm. The dendrites are the fibers that receive messages from other cells. And the dendrites on the hand would be your fingers. So wiggle your fingers, those will be the dendrites. And then the arm itself would be the axon, which passes messages away from the cell body to other neurons or to muscles or glands. And then the myelin sheath would be like the skin that covers your arm. So the myelin sheath covers the axon of some neurons, not all of them, but some of them, and it helps to speed neural impulses. The myelin sheath is responsible for helping us be able to, when we're driving down the road, see some children playing with a ball and it goes quickly into the road and somebody runs out there to get it and you're able to slam on your brakes. It's because of the myelin sheath that the message is able to be sent so quickly from your brain to your leg to slam on the brakes. It really helps us to speed our neural impulses. And then the terminal branches of our axons form junctions or connections with other cells. So, quick review. So, what are the fingers? Dendrites, yeah. What's the palm of your hand? The cell body, yeah, the cell's life support center. And then your arm, the axon, good. And then the skin around your arm, the myelin sheath. Good. I hope that helps you when you're trying to remember the structure of a neuron. Oh, great. We have our first iClicker question. So remember, these iClicker questions, instead of you clicking in with your clicker, instead of that, you're going to be going on to eCourseware under the quizzes where you take your exams. And there is a quiz for this Monday for you to review the iClicker questions and enter them into the quiz. I'll tell you, each time you go and you answer one of the iClicker questions, when you answer it, it will tell you if you got the answer correct. If you did not get the answer correct, it'll tell you why it's not correct. And so we've put that in there so that we can help teach you as you're going through your iClicker questions. So let's start with this one. Which structure in neural communication passes messages through its branches to other neurons, muscles, or glands? Is it A, the neuron, B, the dendrite, C, the axon, D, the myelin? Yeah, it's the axon, right? That's the structure that passes messages through its terminal branches to other neurons, muscles, or glands. Now remember, review the other options in each of the questions. Make sure that you know what a neuron is, a dendrite, what myelin is, because oftentimes the quiz questions that you get on your exams will be about the other options, right? So make sure you know them all as you go through the iClicker questions. So let's put it all together. Neurons are the elementary components of the nervous system, and it's our body's speedy electrochemical system, the nervous system. The neuron receives signals through its branching dendrites, the little fingers in your hand, and it sends the signals through its axons. Back out the arm. Some axons are encased in a myelin sheath, kind of like the skin around your arm, which enables faster transmission. Glial cells provide myelin and support, nourish, and protect other neurons. They also may play a role in learning, thinking, and memory. If a combined signal received by a neuron exceeds its minimum threshold, then that neuron fires and it transmits an electrical pulse down its axon through a chemistry to electricity process. The neuron's reaction is an all or none response. So let's go through that more detail. So here's the structure of the neuron. You can see the dendrites, right, which are the little things coming off the cell body, and the dendrites receive messages from other cells. Then there's the cell body itself, the cell's life support center. Then there's the axon that passes messages away from the cell body to other neurons, muscles, or glands. You can see the arrow is like the neural impulse or the action potential, which is electrical signaling traveling down the axon. And then at the very end, you'll see more branches that have little bulbs on them, kind of, and those are the terminal branches of the axon. They form junctions with other cells. You'll also see in the lower right-hand corner, there's an arrow pointing to the myelin sheath, which covers the axon of some neurons, and it helps to speed neural impulses. So an action potential is that brief electrical charge that travels down the axon. The threshold of a neuron is the level of stimulation that's required to trigger a neural impulse in that neuron. The refractory period is a resting pause that occurs after a neuron has fired. That way, subsequent action potentials cannot occur until that axon returns to its resting state. So another eye clicker question. So the period of inactivity after a neuron has fired is called the A, refractory period, B, threshold, C, action potential, D, all or none response. Yeah, that's right, the refractory period. Then what's the threshold? Yeah, it's that limit that the neuron has to get to before it fires, right? The action potential, the signal that travels down the axon, good. And the all or none response. Yeah, neurons either fire or they don't fire. So the all or none response is a neuron's reaction of either firing with a full strength response or not firing. So it either fires full strength or not firing. It's kind of like on and off, on and off. It's all or none. A synapse is that junction between the axon tip of the sending neuron and the dendrite or the cell body of the receiving neuron. The synaptic gap or the synaptic cleft is that tiny gap at the synapse. And I'll show you what that looks like in a few minutes. So here's a picture of a neuron in the upper left-hand corner, and you'll see the box. This is kind of showing that if you were to blow up and zoom in to that box, then you could see what was going on at the level of the axon. So you can see at the bottom in step 1, a neuron stimulation causes a brief change in electrical charge. If it's strong enough, then this opens the gates to allow positively charged sodium ions, represented by the green arrows, to flood into the inside of the axon. And that produces a momentary depolarization called the action potential. You guys can see that, right? The sodium ions are flowing in through the gates, and the inside of the axon is becoming positively charged. It's becoming depolarized. In step 2, this initial depolarization influences the electrical charge of the next portion of the axon. Gates in this neighboring area start to open, allowing positively charged sodium ions to flow in and to depolarize that next section. Meanwhile, other gates that were open in the first part of the axon allow potassium ions to flow out. That's represented by the red arrows, repolarizing the first section of the axon. So you can see in step 2, the action potential is traveling down the axon, and sodium ions are flowing into the next portion, and the previous portion, potassium ions are flowing out. In step 3, the next picture, as the action potential moves speedily down the axon, sodium-potassium pumps in the cell membrane finish restoring the first section of the axon to its resting potential. So here is a figure that represents the neural impulse. And on the x-axis, we have time in milliseconds. And on the y-axis, we have the axon membrane's electrical charge in millivolts. And you can see here, this is the representation of an action potential and the voltage that's happening on the inside of the neural cell. And you can see this neuron had a resting potential of about minus 70, and neural stimulation caused an electrical charge to go above the minus 55 millivolt threshold. And as soon as it hit that threshold, then that neuron fired, right? It triggered an action potential. And you can see the big spike, and that's the action potential. You can see as the electrical charge in the axon starts to become more negative again, right? It's depolarizing. It depolarizes a little bit below its resting potential to this area where at the end where there's a dip right before it comes back to its resting potential. What is that dip called? Yeah, that's the refractory period, right? Where the voltage went below the resting potential to let that neuron rest for a minute before it gets back to the resting potential. That keeps the neuron from continually being excited, such as would happen in really bad seizures and things like that. So how do nerve cells communicate with other nerve cells? How do they talk to each other? How do they communicate with one another? Well, the neuron receives signals from other neurons, a bunch of other neurons, and some of the other neurons are telling it to fire, and some of the other neurons are telling it not to fire. So it takes those combined signals, and when the threshold of the neuron is reached, the action potential starts moving down the axon. It either fires or it does not fire. More stimulation of that neuron is not going to do anything. It's an all or none response. It's not a graded response. It's an all or none response. The action potential travels down the axon from the cell body to the terminal branches of the axon. And then the signal is transmitted to another cell from the terminal branches of the sending cell neuron to the dendrites or cell body of the receiving neuron. But first, before that signal can be transmitted to another cell, that signal has to find a way to cross the synaptic gap between the cells. So let's see what that looks like. So how do neurons communicate? We can see our neuron again at the top, our sending neuron, and it's meeting up. It has an action potential that's then working on another neuron. And you can see it is axon terminals are meeting at the cell body and dendrites of a receiving neuron. So in step one, an electrical impulse or an action potential travels down the neuron's axon until it reaches a tiny junction known as the synapse. Then you can follow that arrow down into the lower left-hand corner where you can see what it would look like if we zoomed in right at the level between the sending neuron's axon terminal and the cell body or the dendrite of the receiving neuron. And so you can see the action potentials travel down to the axon terminal, and you'll see these little kind of bubble-looking things called vesicles. And inside those vesicles, as they're moving towards the receiving neuron, you can see there's little green dots, and those are representative of neurotransmitters. And so in step two, when an action potential reaches an axon's end, its terminal, it stimulates the release of neurotransmitter molecules. And depending on the neuron, it will be different neurotransmitter molecules. These molecules then cross the synaptic gap and they bind to receptor sites on the receiving neurons. So you can kind of see the little divots in the receiving sites. Those are representing the receptor sites on the receiving neuron. And this allows electrically charged atoms to enter the receiving neuron and excite the receiving neuron or inhibit the receiving neuron. And so it either excites a new action potential or it would act to inhibit a new action potential. Now, in step three, you'll see that sometimes there's excess neurotransmitters. And in fact, always there's going to be some excess neurotransmitter in the synaptic gap. And so it can be reabsorbed, a process that's called reuptake, kind of like our reduce, reuse, recycle. The neuron is like, wow, it took me a lot of energy to make these neurotransmitters. I'm going to move them back into my axon terminal, and it reuptakes them. So some of the neurotransmitter will drift away outside of the synaptic gap, or some of it gets broken down by enzymes that help to break down the neurotransmitter so it stops exciting or inhibiting the receiving neuron. So there's three different processes that can happen with excess neurotransmitters. They can be reabsorbed or reuptaked, they can just drift away, or they can be broken down by enzymes. So what are neurotransmitters? So neurotransmitters are chemical messengers that cross the synaptic gaps between neurons. They're released by the sending neuron, and then they travel across that synaptic gap and they bind to receptor sites on the receiving neuron. That receiving neuron may or may not generate a neural impulse, right? Depending on whether the neurons that were sending the messages to it, but depending on their sum of the activity that it was receiving. Reuptake is that neurotransmitters reabsorption by the sending neuron, kind of like our reduce, reuse, recycle. And they all begin with R, reuptake, reduce, reuse, recycle. So that's a way for you to remember what reuptake is. So Dr. Myers asks us, well, how do neurotransmitters influence behavior? And how do drugs and other chemicals affect neurotransmission? Well, particular neurotransmitters influence specific behaviors and emotions. Acetylcholine enables muscle action, as well as learning and memory. Our endorphins are natural opiate-like neurotransmitters, and they are linked to pleasure and release. They're released in response to pain and exercise. Have y'all ever really enjoyed working out or running? I'm sure there's a few of you that are listening to me who are like, no, Dr. Molly, I prefer being on the couch watching Netflix. And some of you are like, yes, running is my jam. Well, sometimes you'll hear people talk about the runner's high, that they kind of get this euphoric feeling, and that comes from the endorphins that have been released during exercise. And they also help us get a kind of a reprieve from pain as well. And I'll talk to you a little bit more about endorphins and endorphin receptors in a little bit. So drugs, both illicit drugs and pharmaceuticals and other chemicals, they affect our brain chemistry at the level of the synapses. So here's some neurotransmitters that influence us. And this is a great table to study so you can know the different neurotransmitters that are important in human functioning. And y'all are probably hearing my cat who has come for a visit. It's very, very early in the morning, and he has come to visit me. I think maybe the birds started to chirp or something, and he's woken up. So you've been greeted by a cat who is 18 years old. He's about the age of some of you in class. So the neurotransmitter, the first one I want to talk about for all of you sports medicine, sports science people, is acetylcholine. Acetylcholine enables muscle action. So it's the neurotransmitter that I learned about when I was in undergrad, when I was studying sports medicine. Learned a lot about acetylcholine. So its function is that it enables muscle action and learning and memory. When it's malfunctioning with Alzheimer's disease, the acetylcholine producing neurons start to deteriorate. And so with Alzheimer's disease, people have memory problems, right? And that's because the acetylcholine producing neurons start to deteriorate. For dopamine, dopamine's function is that it influences movement, learning, attention, as well as emotion. An oversupply of dopamine is linked to the psychotic episodes in schizophrenia. And an undersupply of dopamine is linked to the tremors and decreased mobility that happens in Parkinson's disease. In fact, in the early treatment of schizophrenia, they used traditional antipsychotic medications that over time, people with schizophrenia started to develop some symptoms called tardive dyskinesia, which is a very difficult time kind of starting the process of movement or walking. And it's one of the symptoms of Parkinson's disease. And so one of the antipsychotics that was used to treat schizophrenia caused the patients to have the symptoms of Parkinson's. The next neurotransmitter, many of you, I'm sure, have heard not in this class, but also on TV, you hear about it a lot, is serotonin. Serotonin affects mood, hunger, sleep, and arousal. An undersupply of serotonin is linked to depression. And some drugs that raise serotonin levels are used to treat depression, like the selective serotonin reuptake inhibitors. So you guys, we were talking about how different neurotransmitters are handled at the synaptic gap, right? Well, the pharmaceutical medications that are SSRIs, or selective serotonin reuptake inhibitors, they are at the synaptic gap blocking the reuptake of serotonin so that it stays in the gap longer to act on the receiving neuron. See, all of this is important. I know it seems like, Dr. Molly, why are you teaching us about this biology stuff? I'm teaching it to you so that you can understand how our body works, how our body is impacted by our brain, as well as our nervous system and our endocrine system, we'll talk about in a few minutes. Now, norepinephrine is another neurotransmitter, and its function is to help us control our alertness and our arousal. An undersupply of norepinephrine can also cause depressed mood. And some of the other medications that are used to treat depression are SNRIs, serotonin and norepinephrine reuptake inhibitors. GABA, or gamma-aminobutyric acid, is a major inhibitory neurotransmitter. And its undersupply of GABA is linked to seizures, tremors, as well as insomnia. Glutamate is a major excitatory neurotransmitter, and it's involved in memory. An oversupply of glutamate can overstimulate the brain, and it can produce in people migraines or seizures. This is the reason that some people are not able to tolerate some types of Asian cuisines that people use MSG, monosodium glutamate, in food. And so some of you may be sensitive to monosodium glutamate. And monosodium glutamate can sometimes cause headaches with people, and also it can make your GI system overreactive as well, which is never fun. So MSG glutamate is a product of monosodium glutamate when it is broken down in the digestive system. And some people's GI systems can't tolerate it, and they can get headaches. Endorphins are our next neurotransmitters we're going to talk about. I told you we would. The function of endorphins are that they influence the perception of pain as well as pleasure. So endorphins are endogenous. They're inside our body. There's also different types of pharmaceuticals and illicit drugs that act at the endorphin receptors. And an oversupply of opiate drugs, which act on the endorphin receptors, can suppress the body's natural endorphin supply. Has anybody in here ever had surgery? Yeah, if you've ever had surgery, you'll know they're really careful about tapering you off of your pain medication. Because when you take exogenous, outside of your body, things that are not made from your body, exogenous pain medications or opiates that act on the endorphin receptors in your body, what happens is that your body starts to make less of the endogenous inside of your body endorphins. It starts to downregulate them. And it's because your body doesn't need as much endorphins because it's getting it from outside the body. And so when you're taking pain medications, you want to lots of times slowly start tapering them off because your body needs to kind of ramp back up its own production of the natural endorphins. So sometimes people will say, oh my gosh, after I got off my pain medication, it feels like my pain is worse than it was before I started taking it. That's because that sort of natural endorphins have been downregulated, and your body needs some time to start making that supply again. So that is an explanation of endorphins, and it's one of the reasons why we currently have an opiate crisis, because your body starts to then want more of the opiate drugs for the same amount of pain relief, and so people start taking more of them, and even though they're no longer in pain because of the surgery, when they try to start just giving off of them, they start experiencing pain, and so they continue to take them, and then they start taking more and more. So here's a great iClicker question. Gerald's grandmother suffers from Alzheimer's disease and exhibits symptoms of memory loss. Does anybody here have somebody in their life that has Alzheimer's disease? Yeah, it's really hard to watch. And if you haven't seen the story The Notebook, it's a really sweet story about a woman who has Alzheimer's disease. If you haven't seen it, it's a great kind of sweet rendition of talking about how a family deals with another loved one's diagnosis of Alzheimer's disease. So she suffers from Alzheimer's disease, and she exhibits symptoms of memory loss. Which neurotransmitter is likely impaired? Is it A, GABA, B, serotonin, C, dopamine, or D, acetylcholine? Yeah, acetylcholine. What was GABA? It was the inhibitory neurotransmitter. Serotonin? If we don't have enough, we start to feel depressed. How about dopamine? An oversupply in the psychotic episodes of schizophrenia? And not enough dopamine in Parkinson's disease, because a particular area of the brain that produces dopamine, the substantia nigra in the brain, starts to deteriorate in Parkinson's disease, and there's not then enough dopamine. And so you'll hear sometimes people who have Parkinson's disease will take a medication called L-Dopa so that the body can metabolize it to increase dopamine levels. So now we're going to talk about how drugs and other chemicals alter neurotransmission. Well, drugs, both illicit and pharmaceutical drugs, and other chemicals affect our brain chemistry, often by either exciting or inhibiting neurons firing. Agonists are molecules that increase a neurotransmitter's action. They act at the receptor level and they increase a particular neurotransmitter's action. Antagonists are molecules that inhibit or block a neurotransmitter's action. So, for example, opioids, morphine is a full agonist of the endorphin receptor, right, of endorphins. And so it increases the pain relieving qualities of endorphins. Antagonists are molecules that inhibit or block a neurotransmitter's action. So y'all have heard that sometimes people who become addicted to morphine or heroin that act on the opioid receptors or endorphin receptors will be given antagonists, like if they've overdosed at the ER, they'll give them naloxone, which is a molecule that then blocks that neurotransmitter's action. And so it binds instead to the receptor very strongly, and it keeps the heroin or the morphine from binding to the endorphin receptor. So naloxone is a type of antagonist. And it's antagonists particularly that's used to help in heroin overdose. Then sometimes they'll give a partial agonist to help treat people who are trying to recover from a heroin addiction, something that acts a little bit on those receptors, but not as much as heroin would. So there's some other medications that they will give people, and the federal government pays for them to be on the medication, and it helps them slowly get used to not having the full agonist, the heroin, acting on the opioid receptor. Instead, it becomes a partial agonist that does not activate the receptor in the receiving neuron as much, so they get a little bit of the benefit, but not as much, and it's less addictive. So next, Dr. Myers asks us, what are the functions of the nervous system's main divisions, and what are the three main types of neurons? Well, as I already said, our nervous system is our body's speedy communication network. Neurons send messages super, super fast, right? And it consists of nerve cells of the central nervous system, and the CNS consists of the brain and the spinal cord. And it also consists of nerve cells of the peripheral nervous system, the PNS, which are the sensory and motor neurons that connect the central nervous system to the rest of the body. The peripheral nervous system gathers and transmits information, and it's divided into the somatic nervous system and the autonomic nervous system. So the nervous system is divided into the central nervous system and the peripheral nervous system. And the peripheral nervous system is divided into the somatic nervous system and the autonomic nervous system. Nerves are bundled axons that form neural cables that connect our central nervous system with our muscles, glands, and sense organs. So here's a great figure representation. So you can see this is a hierarchy. And you remember in our memory chapter, I said that hierarchies are really helpful in helping us learn information. So definitely spend I would spend a minute or 30 seconds, but preferably a minute, really studying this, because this will help you kind of have a roadmap of the nervous system. So you can see at the top in blue is the nervous system, and it's divided on the left, the peripheral nervous system, and on the right in green, the central nervous system. And you can see the central nervous system consists in green of the brain and the spinal cord. Whereas on the left, you'll see the peripheral nervous system, and you'll see all those nerves going out to different areas of the body, right? The peripheral nervous system is divided into the somatic nervous system and the autonomic nervous system. The autonomic nervous system on the left controls our self-regulated actions of internal organs and glands. And the autonomic nervous system is divided as well. The autonomic nervous system is divided into the sympathetic nervous system, which arouses the body, and the parasympathetic nervous system, which calms the body. The somatic nervous system is divided into sensory input and motor output, and the motor output controls our skeletal muscles. So information travels through 3 types of neurons. There's sensory or afferent neurons that carry messages from our body tissues and our sensory receptors inward to the spinal cord and brain for processing. There's motor efferent or efferent neurons, and they carry instructions from our central nervous system out to the body's muscles and glands. Inner neurons reside within the brain and the spinal cord, and they communicate with one another, and they process information between the sensory input and the motor output. So which type of cell communicates within the central nervous system, and it processes information between incoming sensory input and motor output? And so A, glial cells, B, motor neurons, C, interneurons, or D, sensory neurons. Did I do that right? A, glial cells, B, motor neurons, C, interneurons, and D, sensory neurons. Yeah, C, interneurons. Great. Don't forget to review your other options. All right. Now we're going to talk about the 2 parts of the peripheral nervous system. The somatic nervous system is the PNS division that controls the body's skeletal muscles and carries sensory input as well. I would add that to my slide if I were you. The autonomic nervous system is the peripheral nervous system division that controls the glands and the muscles of the internal organs. And the autonomic nervous system is divided then into the sympathetic nervous system, which is arousing, and the parasympathetic nervous system that's calming. So which of the following enables voluntary control of our skeletal muscles? Is it A, the autonomic nervous system, B, the somatic nervous system, C, the sympathetic nervous system, or D, the parasympathetic nervous system? Which of the following enables voluntary control of our skeletal muscles? Yeah, it's somatic nervous system. Excellent. So I said that the autonomic nervous system has dual functions. There's the arousing function and the calming function, right? The sympathetic nervous system, the sympathetic division, arouses and it expends energy and enables voluntary control of our skeletal muscles. The parasympathetic subdivision calms and conserves energy, allowing routine maintenance activity and controls involuntary muscles and glands. So I really want to make this as organic as possible. And so in this lecture, I am going to tell you a little bit about myself and give some examples, and I'm not going to take out the ums and uhs and things like that. So just if you're noticing, I meant to start the lecture talking about that, but I wanted to feel like we're talking person to person so that you can hear me make all my mistakes and be human. So I wanted to let you know that. Next, I just want to tell you a little bit of story about me. So I love to go hiking, and I particularly love to go on a picnic. And so I love, when I lived in California, to go picnicking up on the areas of the mountains where they were kind of have fire lanes where in case there were fires that the firemen could come up and put out brush fires. And so I would on Saturdays love to go hiking in the mountains, in the Santa Monica Mountains, and you could see the ocean from the top of the mountains. And so it was just beautiful. So I would love to on Saturdays pack up a picnic and go on these amazing hikes. And so sometimes I would invite friends to join me. And so we would be out on our hike and just really enjoying our hike and sit down for our picnic. And you can see on the right-hand side of the figure here, the parasympathetic nervous system would be really activated, right? It would be really calming. We'd sit down. Our pupils would contract. We're really just paying attention to one another. We're talking. Our heartbeat starts to slow. The stress of the city starts to melt away. Our heartbeat slows. We're eating, and we're able to start kind of having our digestion start. The parasympathetic nervous system is working on our stomach, and it's starting to stimulate our gallbladder to release enzymes to help us digest our food. If we needed to, we could get up and go use the restroom and come back and just enjoy this picnic. And if we were really into that person we were having this picnic with, the parasympathetic nervous system would allow blood flow to our sex organs, right? It would be easy to become sexually aroused. This beautiful view of the ocean, relaxing picnic, just an amazing sight, right? Well, we're enjoying our picnic on this one Saturday, and all of a sudden, oh my gosh, we're terrified. We look up and there is a mountain lion. All of a sudden, we're in fight, fright, or freeze. Our sympathetic nervous system is totally arousing our body. And you can see in the upper left-hand corner, our pupils are starting to dilate. So it can see where do we need to run if we're going to run, right? It really opens up so it can really take in the whole scene. Our heart starts to accelerate. Our heartbeat starts to pump to try to get blood to our muscles, to our brain, so that we can start moving if we need to. Our stomach is like, I do not need to be digesting right now, so I'm going to stop digesting. So the sympathetic nervous system inhibits digestion. The pancreas stops releasing its enzymes. The liver, though, starts to stimulate glucose release because that glucose may be needed by the muscles to start running in the other direction, and also for our brain to start thinking, what should we do here? The adrenal glands that lie above the kidneys start to secrete epinephrine and norepinephrine, which really set off that fight, fright, or freeze reaction. Our bladder starts to relax. It's not time to go out into the woods and release your urine. And what's the last thing? It says stimulates ejaculation in the male. Well, this doesn't seem very helpful. I do not want to ejaculate to the mountain lion, right? So you're wondering, probably like I was when I was in medical school, how does that make sense? That when I am completely aroused and taken aback by a situation, why does it make sense for me then to ejaculate? Well, it's actually that you can't ejaculate from the sympathetic nervous system unless you first have been really calm through the parasympathetic nervous system. So let me give you an example of this. So in high school, there's a young high school student, and the parents are going to be working late one night. And so the young high school student's like, wow, I'm really into this person. I think I'm going to invite this person over to come hang out with me. And even though this teenager knows that this person is not supposed to be in their bedroom, they think this is the perfect opportunity to go upstairs and have a little picnic on their bed in their bedroom and close the door so that none of the other siblings will know. And so they go upstairs, they invite their friend over after school, and the friend and the other high schooler, they're having a great time, having a little snacks, maybe a little hot Cheetos, some Orange Crush, or some Coca-Cola, and they're just having a great time. And so they start really enjoying each other, put on some music, some Barry White or something, and all of a sudden they're really kind of getting in the mood, and they're just having just such a great time, and they're getting on the bed, and they're starting to make out, and you can imagine the parasympathetic nervous system at this point is really activated, right? Really calm. Their sex organs are able to be engorged with blood, and then all of a sudden, the door of the bedroom swings open, and the sympathetic nervous system immediately goes into action. And when this happens, sometimes, unfortunately, this is the moment where the person with the penis ejaculates. Not wanting to, but because they are so surprised and overcome by the sympathetic nervous system. So that is when the sympathetic nervous system causes ejaculation. Sometimes most inconveniently. All right, so let's go to another eye clicker question. Hassan is nervous for an oral presentation. Any of you all get nervous during oral presentations? I think oral comm is for some people their most dreaded class. So Hassan is nervous for an oral presentation. Some of you may go like, yeah, I get it. His heart is beating rapidly, his palms are sweaty, and his breathing has increased. Which part of the nervous system would have been activated in Hassan? Is it A, the central nervous system, B, the somatic nervous system, C, the sympathetic nervous system, or D, the parasympathetic nervous system? Which part? His heart's beating rapidly, his breathing has increased, his palms are sweaty. Yeah, the sympathetic nervous system. Just like when Dr. Mully was face to face with the mountain lion in Southern California. Sympathetic nervous system was a firing. All right, so let's talk a little bit about the central nervous system. By one estimate, a researcher named Azevedo and his colleagues, the adult brain has some 86 billion neurons. 86 billion. And the brain consists of these work group clusters called neural networks that share function. The spinal cord is another part of the central nervous system, and it's a two-way information highway connecting the peripheral nervous system and the brain. The ascending, or going up neural fibers, are sending up sensory information, and the descending fibers are sending back motor control information. Reflexes are simple automatic responses to stimuli, and they're controlled by neural pathways. So here's a great figure of a simple reflex. You can see this in the lower left-hand corner, there's a candle, and there is an individual with their finger over the candle flame. So you can see in step one, in this simple hand withdrawal reflex, information is carried from the receptors in the skin along a sensory neuron, and you can see that it's the red neuron, and you can see the red arrow, and that sensory neuron carries that incoming information to the spinal cord. From there, you can see the cell body is resting in that little area there, the ganglion of the sensory neuron. It's the little kind of a swollen area before it gets to the spinal cord itself. So there's the sensory neuron, and then it meets in the middle of the spinal cord with the interneuron. And so from there, the message gets sent from the sensory neuron to the interneuron. And then it's passed via the interneuron to the motor neuron, which is then that blue neuron in the blue area that leads to the muscles in the hand and the forearm, which would cause the finger to extend, right? So there's this sensory information that comes in from the stimulus from outside the world. The skin receptor gets the message. It sends it to the spinal cord. Then it meets an interneuron. Then it synapses in the spinal cord with a motor neuron that sends the outgoing information that tells the muscle to contract. Step 2, because this reflex involves only the spinal cord, the hand jerks away from the candle flame even before information about the event has reached the brain, causing the experience of pain. So thank goodness for simple reflexes, right? Like we can withdraw our finger from the flame before we ever even get a sensation of pain, right? And that's all because of a simple reflex. The fact that the sensory neuron is able to connect to the interneuron within the spinal cord and connect to the motor neuron to say, move those muscles away so that you don't get burnt. All right. So that was our journey talking about the nervous system. If you have any questions, I've opened up in eCourseWare, in the discussion boards, areas for you to ask questions about each of the chapters. So there's some there's a topic under a forum for chapter 2 that you can ask any questions and I'll answer them about biology and behavior. So if you have any questions about the nervous system, things that I haven't covered, things that you want to know, please go to eCourseWare and post it on the discussion board. Next, we're going to talk about the endocrine system. So Dr. Myers asks us, how does the endocrine system transmit information and interact with the nervous system? Well, the endocrine system is our body's slow chemical communication system. The endocrine system is the body's slow chemical communication system. What was the body's fast chemical communication system? Yeah, that was the nervous system. Good. Yeah, so the endocrine system is our body's slow chemical communication system. It's made up of a set of glands that secrete hormones into our bloodstream. And hormones are just chemical messengers that are manufactured by the endocrine glands. They travel through our bloodstream and they affect other tissues, including the brain. Some hormones are chemically identical to neurotransmitters. So what are some of the endocrine glands? Well, the adrenal glands are a pair of endocrine glands that are situated above the kidneys. Adrenal. Renal is the term for kidney. Adrenal glands. They lie right above the kidneys. And they secrete the hormones epinephrine and norepinephrine that are so important for the fight, flight, or freeze response. They help arouse the body in times of stress, like during activation of the sympathetic nervous system. The pituitary gland are the endocrine system's most influential gland. They're under the influence of it's under the influence of the hypothalamus, which is a portion of the brain. Y'all remember learning about that, the hypothalamus. And the pituitary gland regulates our growth. It also acts as the master gland and helps to control other endocrine glands. So the endocrine system is a set of glands that secrete hormones into the bloodstream, and those hormones travel through the body and they affect other tissues, including the brain. The pituitary is the master gland that influences hormone release by other glands, including the adrenal glands. In an intricate feedback system, the brain's hypothalamus influences the pituitary gland, which then influences other glands, which release their hormones and influence the brain. So it's a really nice, intricate feedback system. So the brain acts on the pituitary, which acts on other glands, which release hormones that act on the body and the brain. So here's some endocrine glands on the right-hand side. You can see this figure. At the top on the left is a part of the brain. It's a brain region that controls the pituitary gland, the hypothalamus. It lies right under the thalamus, the hypothalamus, the brain region that controls the pituitary gland. The pituitary gland, then, is the master gland. It secretes many different hormones, some of which affect other glands. On the right, you'll see the parathyroids. The parathyroid glands help regulate the level of calcium that's in our blood. The pancreas is also an endocrine gland, and it regulates the level of sugar in the blood. People who have diabetes oftentimes have a problem with a portion of the pancreas called the islet of Langerhans, and they have a very difficult time regulating the level of sugar in the blood. And so they have to test their blood sugar by pricking their finger and using test strips to measure their level of sugar in the blood. And it's really important to keep the level of the sugar in the blood constant because it's really important for our body functioning, including our brain. Then on the right, you'll also see the ovaries are an endocrine gland, and the ovaries are responsible for secreting female sex hormones. On the left side of the figure, you'll see the testes are also an endocrine gland. They secrete the male sex hormones. Then there's the adrenal glands we were talking about. The inner part of the adrenals help trigger the fight or flight response, fight, flight, or freeze response. And the thyroid gland affects our metabolism. And so you've heard about some people who maybe have hyperthyroidism, where they have a really, really fast metabolism. And sometimes you'll meet people who are hyperthyroid and they can eat anything they want. They're hungry all the time. Sometimes they're kind of jittery. People who are hypothyroid, right, they tend to be more lethargic. Weight gain is a common side effect of having hypothyroidism because their metabolism is impacted. So this feedback system between the brain and the pituitary, the other endocrine glands that release their hormones that impact the body and the brain, this really reveals the intimate connection between our nervous system, right? In this case, the hypothalamus portion of our brain, and the endocrine system, the pituitary gland and the other endocrine glands. Okay, so hopefully that was a good quick review of the endocrine system, our body's slow chemical messenger system. Now it's time for us to really turn to talk about how the brain was come to be understood. What sort of tools of discovery have been used over time to help us study the brain and have our heads examined? So how do neuroscientists study the brain's connections to behavior and to our minds? So how do neuroscientists study the brain's connections to how we behave and how we think and feel? Scientists can selectively destroy or electrically, chemically, or magnetically stimulate brain tissue using different techniques. A lesion is a naturally or experimentally caused destruction of brain tissue. Sometimes if someone has a part of their brain that is firing too frequently and causing seizures, they'll go in and they will cause destruction of that area of brain tissue so that that part of the brain will stop sending these messages that are causing the seizures. So sometimes a brain lesion can be caused by a cancer in the brain or a blockage of a blood vessel, as in a stroke. An electroencephalogram, or an EEG, has anybody had an EEG? Maybe somebody here might have had a sleep study for sleep apnea or sleep problems, insomnia. An EEG is an amplified recording of the waves of electrical activity that sweep across the brain's surface. And these waves of activity are measured by having electrodes placed on the scalp. and they put all these little electrodes on your scalp with this gel, and they connect you to all these wires. And in a sleep study, they then ask you to go to sleep like you normally would go to sleep at home, and they watch your brain activity and record the brain activity to see if there's problems with it. A positron emission tomography scan, or a PET scan, is a visual display of brain activity that detects where a radioactive form of glucose goes while the brain performs a given task. So people are able to study the brain's functioning. And so they can give someone a task to do and watch the scan to see the areas of the brain that are using up the glucose because they're working during that task. PET scans are really cool, and I've enjoyed getting to watch them at Le Bonheur during some of the studies that they've done on children there and at St. Jude, children with cancer, and how it impacts different areas of their brain. So here is a picture of a woman getting a what? Yes, an EEG, right? She's getting an EEG, and you can see these amplified waves that are being recorded that are showing her brain activity. An MRI, or magnetic resonance imaging, is a technique that uses magnetic fields and radio waves to produce computer-generated images of soft tissue. An MRI scan shows brain anatomy, right? So it shows the structure of the brain. An fMRI, or a functional MRI, is a technique for revealing blood flow, and therefore brain activity by comparing successive scans of MRIs. The fMRI scan shows brain function as well as its structure. So an MRI is really used, it's static, it's used to show brain structure, whereas an fMRI shows brain function as well as its structure. Which technique involves the usage of magnetic fields and radio waves to produce computerized images of soft brain tissue? Is it A, lesion, B, EEG, C, MRI, or D, PET scan? Yep, it's an MRI. Have you ever had an MRI? Oh my goodness, it is so loud. And when you get an MRI, they make sure, because they're using magnets, that you don't wear any jewelry, that you don't have any metal on your body, in your pockets, or anything, because it would quickly leave wherever it was and be attracted to the extremely strong magnet, which you can imagine may mean that it is ripping out of certain areas of tissue in your body, and so it's super important. They make you sign a form that you don't have any metal on you at the time when you have an MRI, but sometimes people have MRIs to check for the structure of their brain if you're having severe migraines, or if they think you may have some sort of degenerative neurological disease. Recently, I've been tested because of my symptoms and my autoimmune problems to see if I may have MS, multiple sclerosis, which they can see lesions in your brain, particular types of lesions in your brain if you have MS, multiple sclerosis, which is not what I have. So this is a great representation of two MRIs. On the left-hand side, you'll see a left arrow pointing at a normal person's MRI of the third ventricle, and you can see the size of the third ventricle. It's kind of like that butterfly-looking dark space in the MRI scan. And on the right-hand side, this is an MRI scan of someone with schizophrenia. And people with schizophrenia have these enlarged ventricles. This is the third ventricle of the brain, and you can see the butterfly is quite bigger. And so this is an example of the difference of an MRI between someone on the right who's been diagnosed with schizophrenia and someone on the left who has not. So I told you we were going to talk about some of the older brain structures. So we're getting to that section. We've talked about the nervous system. We've talked about the endocrine system. We've talked about the tools of discovery. And so let's talk a little bit about older brain structures. So what structures make up the brainstem? And what are the functions of the brainstem, the thalamus, the reticular formation, and the cerebellum? Well, there's less complex brain in primitive vertebrates, and they regulate basic survival functions. So primitive vertebrates have less complex brains, right? More complex brains in advanced mammals, including humans, contain the new brain systems, our huge cortex, built on the old brain systems. The brainstem is the oldest and innermost region of the brain. It begins with the spinal cord as the spinal cord swells as it enters the skull. The brainstem is responsible for automatic survival functions. The medulla is at the base of the brainstem, and it controls our heartbeat and our breathing. Our brainstem is a crossover point where most nerves to and from each side of the brain connect with the body's opposite side. So sometimes if we are in a car accident, has anyone ever been in a car accident and hit their head? Sometimes if we are in a car accident and we have a head injury and we have some leaking of blood in our brain, the blood in the nervous system the nervous system doesn't like blood. It causes a lot of inflammation. And so you can have swelling in your brain. And as your brain swells, it starts to put pressure on the only outlet from the skull, which is the area that the brainstem and the medulla are passing through to go out of the skull. And so sometimes the swelling will cause pressure against the medulla, which can cause your heart to stop or you not to be able to breathe. And so sometimes they'll have to release the pressure in your brain by boring a hole in your skull to let some of the pressure come out so that your brain is able to not move down into the lower part of the skull and cause the medulla to get trapped. And so another thing is that if someone has a stroke, right? Lots of times if they have a stroke on, let's say, the left side of the body, right? The left side of their brain, if they have a blockage in a blood vessel on the left side of the brain, they'll have symptoms on the right side of their body, because at the brainstem, the neurons from the left side of the brain cross over to the right side of the body. So here's a pictorial representation of the brainstem and the thalamus. So the brainstem, including the pons and the medulla, is an extension of the spinal cord. The thalamus is attached to the top of the brainstem, and the reticular formation passes through both structures. The reticular formation is really important for alertness and consciousness. And I already told you the medulla was really important for heartbeat and breathing. I love the medulla. It was one of my favorite parts of the brain when I was in medical school, because medulla is its shortened name. Its long name is the medulla oblongata. And I loved its name. I thought it sounded so important, the medulla oblongata. And that's how it helped me remember that it was in charge of the heartbeat and our breathing. And so the medulla, the pons are part of the brainstem. The reticular formation are brain neurons that go up through the brainstem, through the thalamus, and are responsible for alertness and consciousness. And then the thalamus, you'll learn, is the brain sensory control center. And it's located on top of the brainstem, and it directs sensory messages to the cortex of our brain. And then it transmits replies to the cerebellum and the medulla. The reticular formation involves a nerve network that runs through the brainstem into the thalamus, and it filters incoming stimuli, and it relays important information to other brain areas. And like I told you, it plays a really important role in controlling arousal and consciousness. The cerebellum is another part of the brain, and it aids in judgment of time, sound, and texture discrimination, as well as emotional control. The cerebellum coordinates our voluntary movement and output as well as our balance. And it enables our nonverbal learning and memory, our procedural skills like walking, riding a bike. These older brain functions illustrate how much of our brain processes. Excuse me. These older brain functions illustrate how our brain processes and stores most information outside of human awareness, right? So without any sort of cortical involvement. So you can see how the cerebellum is able to keep us balanced, keep us moving. The medulla is able to keep our heart beating and us breathing, right? And so sometimes when people have brain death, they'll talk about their cortex not being active, and they may be in a coma and able to breathe, and their heart's still beating, but they don't have any activity in the part of the brain that is kind of what makes us seem more human, right? The cortical regions of the brain. And so people can stay alive in comas for long periods of time. And so it can be very difficult for family members financially and emotionally to decide what to do when a family member's flatlined on their brain activity. It's not showing any cortical activity, and yet they're still breathing and their heart is still beating. It makes it really difficult for families to make decisions around end of life. So which brain structure enables basic functions like nonverbal learning, skill memory, and coordination? Is it the A, thalamus, B, reticular formation, C, pons, or D, cerebellum? Yeah, cerebellum. And I like to remember cerebellum. I think it sounds so beautiful. It reminds me of dancers. I really love the Nutcracker and Tchaikovsky's music in the Nutcracker. And there's some of these bell sounds that are really sweetly put through that score of music in the Nutcracker. If you've never seen it, it's absolutely amazing. It's the story of Clara, and it's a really wonderful kind of holiday story that oftentimes is performed by the ballet. So I like to remember the cerebellum, like the little bell music, and dancers, and the cerebellum is involved in balance and coordination, and it's very well developed in dancers. All right, so that was our first lecture. So that's Monday's lecture, and I will pick up here for Wednesday's lecture, where I will tell you all about the limbic system, which is a really cool part of the brain. It's linked to emotions and drives, including sex drives. So you can imagine I know a lot about the limbic system because of my area of research. So I hope that you are doing well. And I will look forward to talking with you again on Wednesday. Don't forget to go and ask any questions on the discussion board, and don't forget to go take your iClicker questions for today. The iClicker questions, when you answer them, if you get it correct, it will tell you. If you get it incorrect, it will tell you why you got it wrong. And I'll see you soon. Bye.